Welcome everyone to EL 164 online. Today we're going to talk about math instructions. Woot woot! And this is going to be the last lecture for the series. Again, I appreciate everyone's patience and understanding for the situation. I'm doing a few things that I can to make sure you guys are getting some points from extra credit and whatnot. So take a look at that extra credit work when you get a chance. I think you guys will find hopefully all those answers to come pretty easy when you get the time to analyze each question and find the answers. So look me up if there's any questions or concerns with any of those, and we can certainly go through those. Okay. Starting with today's lecture, we're going into mathematics. We're going to talk about math instruction. This is going to be following along with Chapter 11. Again, keep in mind we're utilizing the Chapter 11, which is based on the Slick 500 platform, and actually I'm teaching to the RS Logix 5000 platform. So if you remember correctly, that is a difference between a 16-bit word operation versus a 32-bit word operation. Okay, without any further ado, I'm going to go ahead and start plowing through some of this. So talking about math instructions. So a math instruction, we're looking at here, we've got a couple of things here. We've got the source A and source B, and usually a destination. What that infers is that the comparison instruction, like the comparison instruction, it's always A, then B, and with the results in destination. What does that mean? So as I put an example down here below, source A is equal to 10, source B equals to 2, with the results of source A on top of the division, source B on the bottom side of the division, and destination equal to destination. So here we are, 10 divided by 2 obviously equals 5, and the destination is the results. So hopefully, and this is true for all the math instructions, source A, then B, results and destination. Again, like many applications in the PLC, they all utilize the data tables, and you can use any variety of data tables. So what I did is I threw an example up here on a 5000 instruction, and some of the different tools you can see there. You see a double integer, you see a number, you see a timer accumulated value, a counter accumulated value, and another double integer. I mean, these are just a few of the different tools that are available to us. As you'll see here, you'll see integers are available, double integers, timers, counters, I/O tables. You can use the input table, output table, and numbers in the decimal form, binary form, and in the hex form. So basically, the math functions perform arithmetic functions on values, on registers, on counters, timers, you name it. So essentially, when we close the switch here, we close this contact, and the sub is considered an output because it's looking for an input to enable it. So that's kind of why they call it output statement. And so it's the output function of the PLC. So here's kind of a generic 500 version of this, and this is what the 5000 block looks like. Very similar, same principles all apply. So you've got the add, the source A, source B, destination. So 3 different locations for information, whether this could be a numeric value, a register value. This could be a numeric value, a register value, and again, this has to be register value. Why? Because you're taking a value and placing it someplace. You have to have someplace to put it. So you can't put a number here and have it, add this plus this has to equal some number. If you have a number here, there's no place for that number to go, so they won't let you put a number there. It's looking for a registered value there. So source A, source B, again, can be a rack location, file address, instructions, trying to give you some ideas on different aspects. Again, if you remember our first unit where we talked to 500, you'll see some of these addresses, and I felt this was valuable enough to keep in there. So again, here's some more destination fields. And then again, I threw this in there so we can actually look at, again, what does all that include. So you can use any different type of data types of words as illustrated here again. So I'm kind of flipping through this. This is kind of a duplicate here, just reiterating that yes, you can use whatever you want. Things to keep in mind. What do we have to do when we use a binary? We have to put a 2 pound sign in front of the numeric value of ones and zeros. If we want to use a hexadecimal format, we need to put a 16 pound sign and a series of A, B, C, D, E, F, or 0 through 9. Just keep those 2 points in mind. So the first math instruction we're looking at here is called the compute instruction. What the compute instruction allows us to do is to develop our own expression any way we want to do it. So we don't have to use a specific math function like add, subtract, multiply, all these different blocks to do a math function. We can do all those in one function. If we have to do an add, a subtract equation, and with a multiplication, division in there, we can do it all in one. So here we're talking about the compute instruction. As you can see here, I threw multiple different components in this: double integers, do decimal value, a timer accumulated value, a counter accumulated value. So you got a lot of different choices here. This is in the 5000 or RS Logix 5000 form. This here again is in the 500 format. So next we're going to talk about the addition instruction. So here we are looking at the format in the RS5000. If you're following along in the book, you'll see something very similar, only in the 500 version. So here what I'm looking at is the add instruction found under compute/math. You've got the add instruction. Essentially what we're doing here is we close this contact here, and whoops, I'm not in the laser pointer here. We close this contact here, and we'll see this math take place. So we'll take a 0 plus A, B, C, D, and it would put the value here in destination. And here's an illustration of that very thing in what they call the 500 realm there. So 50 plus 25 is 75, so we're going to change this to 49 and 28. So when we close this contact, we end up with 77. Pretty easy peasy there. Easy peasy. Okay, so here they're looking at another application. You'll find this in the book as well, where we got a couple of counters here, and an add statement where they're adding the accumulation value of both those counters together and dumping the value here to N7:1. And here you see that whole thing taking place here in a simulated form. So as soon as that equals 10, bam, your pilot light comes on, and you're in business there. To reset and start over again. Okay, so next thing we're talking about is the status bits. How do those status bits work and why are they so important to us? Okay, status bits. Essentially, well, status bits are indicators for us to know when there's a situation with a number. For instance, in this particular case, the first one we're looking at is a negative. It comes back and gives us a bit that turns on under the status bit. You see SN, that's S is for status, N is for negative, and the negative flag here. I pulled this right out of the book here, so this is right out of the Allen Bradley book here we're looking at here. And so when it sees a negative value here, it makes this guy come on and turning on this negative bit that I just randomly selected. Now, one of the points I want to make that the book was very clear on was the Allen Bradley software, the RS5000 software, does not highlight these bits. So when you're dealing with this in the field, make sure that you're acknowledging this information that it's tied to, not the contact itself, because it does not highlight like this. It just stays this form. Even though this is a negative 13, this bit is on, and it's illustrated to be on by looking at the coil here being on as well. So just be aware of that. So basically, a negative value is in the destination, turns on SN, which is on. So this guy being negative turns him on. So something to consider when you're dealing with subtraction, or maybe even some other forms of dealing with even say a counter. You've got a counter that's starting to count negative. You want to make sure when it goes negative, what? Maybe you reset it to 0, or you put a different value in there so it doesn't go negative. That's something to consider too. Some different options. So things to think about. Next piece of this, the next flag I wanted to talk about was the overflow flag. Now this overflow flag, as you can note here, I pulled it again straight out of the book. The result of math operations result in an overflow. What that means is essentially that we put a number in there greater than what the register can handle. So now, when you're talking 32 bits, you're talking a really large number. When you're talking, say, single integer, you're looking at 128, 127 here, right? When you're talking, some very large numbers, though, like here they're showing us example of a single integer or integer tag. They can be pretty good sized numbers before they actually overflow. But yes, you can overflow those numbers. The way I illustrated this was I took a very large number, made all these F's, just shy of all 8 of them being F, and multiplied by ABCD, excuse me, and that makes for a very, very large number, which definitely I knew for sure it was going to put me in overflow. And so what I wanted to illustrate here is that when we get some value that's overflowed, this SV comes on, and we see, as you can see here, with this coil on, indicating that this SV is on. So the destination is larger than the register could hold, so it turns on SV. So essentially what we're looking at here is that the number that you're looking at isn't necessarily the true number, because it overflowed the register. It went beyond what the register could hold. So what it's doing is it's going past positive, it's going into the negative number, so it went over the top, right? So that's why it's a negative number as well. So it's not an accurate number when it comes to, you couldn't use this number as this multiplied by that equals this. It wouldn't come out properly because of the number of bits available in that destination can't support the number that this times this would equal. Okay, moving on to the next one. The carry flag. The controller sets the carry flag when the results of the math operation result in a generation of carry out of the most significant bit. So what happens, what I'm trying to illustrate here is that when you have a situation such that I've got ABC0, which is smaller than ABCD. So what it's saying is that I am trying to subtract a larger value from a smaller value, And this value that I'm subtracting from is greater, or I'm pulling more from it than there's in that register. So that means that it's pulling, or it's got a carryover from basically pulling another bit from another word to attain a valid number. Well, which is basically telling you that hey, there's definitely a problem here, because this register isn't big enough to handle that kind of information. So the information here, it could be invalid. So by using the carry bit, you can validate that when you see the carry come on, you're validating that number is most accurate. When you see the carry bit on, that means you may have a problem with that number. It might be okay, but you need to be aware that it is a carryover number. So that's why that's set as such. So so when the SSC is on, that output turns on there. So here's the other point I wanted to make with the SSC. So there is a carryover, as you can see, in when I subtract 100 from 1, right? You got to take scratch the 1, make that a 0, make the 1 next to that a 10, and scratch that, make that a 9, and makes that very first number a 10. That's also called carryover, but as you can see here, it doesn't turn this bit on because I'm not exceeding the capability of that word. So that's why it's giving me it's allowing me to do that without triggering the carry. The 0 flag simply just tells us that the register is at 0. It can be used in a lot of different applications, not just in add, subtract, multiply, divide, but it can be used in many different applications just to tell you that there's a 0 in that register. But basically, if it sees a 0 there, it sets a 0 flag and gives you the ability to turn on a bit because it is 0. The subtraction instruction. So subtraction instruction. Here we are. We're looking at compute _ math subtraction. Again, I want to illustrate source A from B. It subtracts B from A here. So it's kind of worded backwards because of the book, but it's always A then B. So A is the source minus B. So here I wanted to illustrate how I could subtract a binary 1 from an integer value of 255, a decimal value of 255, and end up with a value of 0 when it's off, because there's no action that's taking place. And then when it turns on, as you can see here, it subtracts 1 and I get a 254. Pretty cool operation. And here we are looking at an illustration of how that actually works. Okay, looks like we're done with that. And now we're looking at another application where we could use a subtract. They're subtracting the address. What? Subtract the source, I012, from 500 and place it in N7:1. Let's see how this whole thing plays out. So they're turning on a series of 1s and 0s in that input 5 register to get that value in there. Excellent. Multiplication instruction. Okay, let's see here. What do we got going on here? Same idea. So we're looking under Math Compute, under MUL, or multiply, source A by source B, placing results in destination. So we got source A of, I put a bunch of F's in there, and I took it, multiplied it by the timer accumulation value of 1. As you can see, I put a timer in there, accumulator value. And then for the destination, I threw in a double integer 3, and I'm illustrating it in binary. So just showing some of the different aspects that are available for us here. So here, looking at this, we take with the action off, we have completely zeroed out the register, and when I close this contact, I go ahead and I multiply this by this, and what I'll end up with is essentially the same number as this, only in binary. And here's an illustration of how that works in the 500 realm of world. All right, now we got, here's another one to calculate the product of two sources here. So we're looking at multiply A by A times B with a destination of N7 colon 3. Okay, moving into division. Here we are talking about division instructions. So here again under compute/math, we've got the division. Division has a couple of aspects to it that we'll be discussing here in a bit. So the first piece of this is, as you can see here, I have A divided by B. So it's, if you're looking at some sort of math symbol or whatnot, it would be A divided by B, something of that nature. So so it's always A is on top, B is underneath, and destination would be the equals 2. So that's going to be the case. So as soon as we close this contact, we're going to get, as soon as we close this contact here, we're going to get the destination populated with 32 divided by 8. So here we close the contact, 32 divided by 8 equals 4. And here we are, we got an example of that. There we are. Here's another example of A divided by B. $60 divided by 2 is going to be what? Okay, so one of the challenges with the divide statement is that what is the carryover or the remainder? I guess was probably a better statement. Is what is remainder? So Brown and Brad use a term, an instruction called the modulo, or mod command to tell you what the remainder of a division process is. So here in this particular application, we got 10 divided by 3. Everyone knows here 3 times 3 is 9, leaving us a remainder of 1. So we end up with 10 divided by 3 is 33.333, or 10 divided by 3 is the remainder of 1. So another point that we got to be aware of is that we can't divide by 0. Now, there was a time when Allen Bradley had it set up such that the processor would go into a major fault if a divide by 0 took place. Apparently, with their new upgrades, they have decided not to cause a major fault now. So now it's just a minor fault. I thought I would populate that fault down here below so you to see what it's all about. It doesn't stop the program, doesn't stop the processor, doesn't do any of that nature. Just pops up a minor fault saying, hey, we have an issue, something that is pretty easy to get over with. So yeah, dividing by 0 is not a thing. It's mathematically, it's against the laws of mathematics. So shame, shame, shame. Don't do that. It's very bad. The way Allen Bradley handles this situation is, as you can see, they took the source A and dumped it right in the destination. So you do end up with a value in there, but obviously not the correct value. So just make sure you're aware of this. Whenever you divide by 0, it's going to put the source in the destination. So just be aware of that. Here's kind of an example of how that mod works, or mod instruction. Again, under compute math. Essentially, all this mod does then is it spits out the value that's the remainder value. So if you want to know what your division value is, you're going to have to do division. But if you want to know what the mod value or the remainder is, you're going to have to do the module command. And here I kind of illustrated that with the 5000 version. So you don't necessarily have to provide the mod every time you do a division, but I just thought this would be a good opportunity to illustrate exactly how this is done. So again, I've got a division command here where I end up with, when I close this contact, I end up with a 3. As you can see, it just illustrates it as a 3, even though it is a 3.33. Because it's an integer, it's only going to display what? Whole numbers, no, not real numbers. We're not. If we got into real numbers, which, as I said in this class, we typically do not. We could be dealing with 3.33, but we're only dealing with whole numbers. So integers are whole numbers. So we'll stick with those. So the other point that I want to make is that I've added the mod program here. So now I've got 10 divided by 3, and it comes with the value of 1. Now, what does 1 mean? 1 means that is the remainder of 1. So 3 times 3 is 9. Leaving a remainder of 1. So that's where the 1 is coming from. I wanted to further illustrate this by doing 10 divided by 4, excuse me. 10 divided by 4 is, in mathematics, is of course 2.5, or 2 with a remainder of 2. So as you can see here, 4 divides into 10 2 times, so I got a 2 in here. If you're looking at the module side of things, you take 10 divided by 4 is 4 times 2 is 8, leaving a remainder of 2. So I have a remainder of 2 in the module. That's where the 2 comes from. So just to be aware, that's how that works. And here's an illustration of some of that. Okay, other word level math instructions. We're looking at square root. I don't know if many of you have to work with square root much. I know in mathematics, three-phase, and dealing with a few different things in electronics world, you do end up dealing with some square roots. So here we're looking at source value of 16, a destination value of 4. yeah, destination value of 4. So the square root of 16, of course, is 4. So when this contact closes, you'll see that the square root of 16 is, the destination is populated with that value of 4. Pretty straightforward. Again, I can use double integers, I can use counters, timers, hexadecimal, binary. I can use all that sort of different things. So, and here's an illustration of how that works. So compute math again. Here we got the negative. So essentially, as you'd anticipate, this just basically puts a negative sign in front of any value you run through this command. So here we're looking at, as soon as I close this contact, I had 16 in there, and now it makes it a negative 16. And this works for pretty much all the different registers as well. Okay, that was a pretty good illustration. Just to note that if you try to put a negative value to 0, it leaves it at 0. It just doesn't put negative, which makes sense to me. So the final piece of this is the absolute or absolute value instruction. So it takes no matter what numeric value you bring into it, and it sets it to a positive number. Essentially, it doesn't care if it's positive or negative going into it. It's going to be positive coming out. So it's basically, so if I set a negative 16 in there, it would give me a negative or a positive 16 out. So something I talked about a little bit last class period, but I wanted to review it again as a clear instruction. Essentially, if you put a numeric value in a register in this clear function, it zeroes it. This is something used quite frequently in programming. Why does it make sense to put a clear statement in there instead of like move a 0 to that location? The clear, what it does for us is it gives us a clear definition of what we're trying to accomplish. Moving a 0 to a register, yes, definitely, it's fairly clear in the sense that, yes, I'm moving a 0 there to clear out this register. But when you do the function CLR, everybody knows what you're trying to do. You're trying to clear that register out. You want to make sure there is no data left over in that register. So when you start your next math function, your next operation, your register is cleared out and ready to perform the next function. So that's a really, it's just from a programming perspective, it makes a lot of sense to go that route. And here's an example of using that. So here's a few of the points we're skipping out of this chapter. TOD, FRD, basically BCD really isn't used much anymore. I mean, there's a few aspects that will be used, but not a whole lot. And the few places you will be using it, I suspect it'll be an older application, and you're probably using the 500 software or some older version software anyway. So I'm trying to eliminate some of the different areas where I try to be relevant. Things that I've used in the past that I felt were relevant is basically what I try to stick to. Again, with a SCL, the scale with parameters. I have used a few of these parameters, a few of these operations before in the past, but the key is that I don't. It was very rare applications, and this class is designed to get you some basic ideas on how PLC works. I'd really hate to dive into the heavy parameters and the harder parameter programs associated with it that would lead you astray from where I want you to stay focused. So that I've skipped that section as well as 11.7. As I mentioned at the beginning, this is my last lecture. I'm going to be sending this last section out here for this week, and then the following week we'll have our last Unit 4 exam. So you should be looking forward to seeing that in not this coming week, but the following week. As I've mentioned many times, make sure you're staying on top of that online homework. I set this last unit, Unit 4, up to close on Sunday. So unless you have special circumstances, which you need to let me know right away, my goal is to have all that online homework done by Sunday. So that's this Sunday. Let me confirm the date on that. That's going to be April 12th.